Hello. Thanks for joining me today for this webinar on project portfolio ranking and prioritization on steroids. My name is George Hune, founder and president of Data Machines. Data Machines is actually located, not just incorporated, in Delaware, and we recently celebrated our 10th year in business. As a way of background, I became interested in the problem of project selection during my work as a senior research scientist at DuPont and as a consultant in a variety of big and small companies. The seeds of the application that I will be talking about today came during my studies in technology management at Wharton and the University of Pennsylvania. After seeing company after company struggle with these problems and not finding a satisfactory solution in the marketplace, I decided to develop OPSI because it was the tool that I wanted on my desktop. I decided to offer this webinar in particular after reading the thread of a discussion where the person who initiated the discussion asked for ideas about prioritizing projects. Many of the responses in the thread offered ideas for project rankings based on non-quantitative, non-value-adding, and in the end, not very useful metrics when it comes to meaningfully ranking a project portfolio of any significant size. Also, none of them mentioned optimizing a portfolio, an essential part of any project portfolio management program. Why is it essential? Unless you're going to fund and deliver on all the projects on your list, then you need to have a particularly sound and defensible way to pick and choose your projects after you've ranked them. And if you're going to fund and deliver on all your projects on your list, then project ranking is a meaningless exercise since it really has no impact on any business decision. That's why I say that prioritization without optimization is like soup without water, and the best optimization in the world is meaningless without a sound, rigorous, and defensible project ranking system. In other words, just having water doesn't guarantee good soup. All of the ingredients have to be good too. Project prioritization should only be about ranking projects according to the quantifiable value that they bring to the company as defined by the company. Portfolio optimization should only be about maximizing the value of the portfolio of ranked projects based on the constraint limitations like not enough money or not enough resources and tolerance for risk. And that's it. So, our focus is to help our clients pick project portfolios that deliver the highest value to their company within their tolerance for risk. And we do this in two steps. First, by prioritizing projects by running the entire portfolio in thousands of different models that can show both the ranking and the uncertainty distribution around each project. That's the on steroids part. And second, by optimizing the ranked project portfolio against constraints and simultaneously running that portfolio in thousands of simulations to get the distributions of value outcomes for the entire optimized portfolio. The result is what you see here. The curved lines represent the efficient frontiers for the entire portfolio. Efficient frontiers show the maximum outcome for a given input, such as in this case, value versus cost. The green line is the highest possible efficient frontier, the blue line is the most likely efficient frontier, and the red line is the lowest efficient frontier. Each pattern sphere represents an optimized portfolio. The vertical lines represent the best and worst outcomes, and the horizontal bars represent the standard deviations. Essentially, OPSI lets you dial in your business constraints to find different optimal portfolios for millions or billions or even trillions of possible combinations. And because these optimizations are based on the project ranking simulations, the result is that you can see the best outcome, worst outcome, as well as the distribution of potential outcomes around each portfolio. When you click on a bubble, the distribution of outcomes for that portfolio is displayed. If you're using a system that only accepts single values for each project and you can't do simulations, then you won't see this. And if you can't see this, then you don't know where your results are in the distribution. So the result is that you can see both the value and associated risk associated with each portfolio. And, as you will see, all of these results can be obtained in just a few minutes using a few mouse clicks. There's no programming, spreadsheet manipulation, or multiple software applications needed. So now, let's go back to the beginning and talk about the process of getting to here. I'm going to start with the data and the problem of garbage in, garbage out, and then move to modeling and project ranking, the on steroids part, and then move to a short discussion of optimizations and portfolio selections. I made the promise on the invitation to this webinar that it would change the way you think about project portfolio management, and by the end, you'll see why. So, one of the most common questions that I get is, what about the problem of garbage in, garbage out in portfolio modeling? Most of the time, the people that ask me this question are thinking about the accuracy of the business data estimates and the forecasts that are used in a modeling system. But there are really three other questions besides how accurate is the data that need to be considered when it comes to dealing with the garbage in, garbage out problem. The first question is the metric quantifiable, and how does it impact project value? The second one is, what is the precision or uncertainty around the data? And the third one is, how important is the data to our decision? The answer to the question, is the metric quantifiable and does it impact project value, determines whether or not that data should even be considered in the portfolio model. Most of the time, I have found that metrics that aren't quantifiable don't impact business value anyway, so it is an important question to ask from the start. Keeping out non-value adding metrics from the model is the first step to keeping garbage out of the model. Next, the answer to the question, is the data accurate, is really critical because most other portfolio management systems only accept single point data values. So the accuracy of those values is absolutely critical to what comes out in the final analysis. So, if your data is not accurate, the results you get out are going to be garbage regardless of how good your model is. So, the other question that needs to be asked is, what is the precision or uncertainty around the data? Let me use a quick illustration comparing four people throwing darts at a bullseye. The first illustration shows a situation where the person throwing the darts is neither accurate or precise. The second illustration shows a situation where the person throwing darts is extremely precise, but not very accurate. The third illustration shows a situation where the person throwing the darts is accurate, but not very precise. You might say that their precision or uncertainty for hitting the bullseye is about the size of the entire target. And the fourth illustration, of course, shows a situation where the person throwing the darts is both accurate and precise. The garbage in, garbage out problem occurs most often when it is assumed that the data is represented by the last illustration, that is, being both accurate and precise. But this is almost never the case. So while you might be thinking that you have accurate data, you are more likely to have generally accurate data that isn't very precise. In fact, virtually all data that goes into project portfolio management analyses has a great deal of uncertainty around it. Because of this, unless you can account for the uncertainty in your data, your result is likely to be way off target. You might be throwing darts without even knowing where the target is, or whether or not you've even hit it. And it isn't just around the project data that you put into the analysis, it is also around the data that you use in the model itself, such as how you rank your attributes. So, the key takeaway here is to question and understand both the accuracy and the precision or uncertainty around your data. If your system requires an assumption of accuracy without consideration of the uncertainty or precision, then you're likely to end up with a result that may feel accurate and precise, but is in fact inaccurate, imprecise, or both. Furthermore, if you can't see the uncertainty around your results, you won't be able to see either the upside or downside risks associated with your portfolios. So, garbage in, garbage out is one of the big problems in project portfolio management and project ranking. But even if you have great data and you understand the precision around the data, if you have a lousy model, you won't get good results. I call this the gold in, garbage out situation. Ideally, the best situation is to have great data and great analytics to get the best results. However, you can still get excellent results even if you have merely good data but you have great analytics. The results, of course, can only be as good as the data, but at least you'll see the uncertainty in your outcome. Another big problem in project portfolio management in regards to project ranking comes from selecting and using the individual criteria or attributes that you're going to be using to compare and rank your projects. In OPSI, each attribute is associated with both a weight and a rank. The higher the weight, the higher the rank. Attributes with higher weights are proportionally more influential in the ranking than attributes with lower weights. For example, an attribute with the weight of 1,000 will have twice as much influence on the project rankings as an attribute with the weight of 500. Now, Putting aside the challenge of selecting an appropriate set of attributes to begin with, decision makers often have difficulty in selecting attribute weights. I have never met two managers working on the same project portfolio that, in the beginning, want to rank attributes the same way. In general, it is easier for decision makers to agree on a simple ranking of attribute importance. This way, the discussion becomes simply determining which attribute is more important than the other attributes, eliminating that attribute, and then repeating the discussion on the remaining unranked attributes. This is an easier discussion to have as opposed to quantifying exactly how much more or less important one attribute is relative to the other attributes. Again, single value weights can lead to a certain amount of complacency around the precision around those numbers too. When I start to show you what a project prioritization on steroids looks like, I want you to remember the relationship between attribute rank and attribute weight. That is, the higher the weight, the higher the rank. Another important point in regards to a multi-criteria project ranking system is how the raw project data is translated to value in the model. You need to have flexibility so that the model truly reflects the values of the decision makers, including their tolerance for risk. In order to have a project ranking system that truly reflects the opinions of the decision makers, it needs to be able to process different kinds of data in the form that the decision makers require. We accomplish this using attribute forms that allow the decision makers to enter their data in its raw form and select and adjust a utility or value curve to match their preferences. For example, here is the value or utility curve for reward. Note that projects that would have a reward of $100 million have a value of 100 associated with them, and that projects that have a value of $25 million have a value of 0 associated with them. What this says is that the decision maker assigns no value to projects with rewards of $25 million or less, and assigns full value to projects valued at $100 million. The line between them reflects the intermittent values where most of the projects are going to fall. In this example, the utility curve is slightly concave, indicating a preference for higher value projects. This line is easily adjusted by simply control-clicking on the screen. One thing that you'll see in many other project ranking systems is that they try to force in data into artificial 1 to 10 scale linear relationships. In OPSI, you can use many different types of value curves and adjust them any way you want. You can also assign value curves to discontinuous or categorical data, such as colors, locations, therapeutic area, or whatever. In this example, you can see that the value was assigned to technological maturity ranging from embryonic technological maturity, or projects that use technology that is very, very new, to aging technological maturity for projects that use commodity type technology that is very old or very well known. So, for project prioritization on steroids, you want to have a model that accepts all different kinds of value-adding data in a way that the decision maker wants to enter it. The closer your model is to the actual data, the better it's going to be. Now, let's take a look at how you enter data for projects that includes the uncertainty associated with the project data. In OPSI, projects are stored in a portfolio form. The portfolio form displays the project name, the most likely value, the high value and the low value, and the project data in the attribute columns that are associated with each attribute in the decision model that we saw earlier. At the bottom of each column, the associated sum, average, and standard deviation are automatically calculated for you. When you optimize a portfolio for value, you're trying to pick the set of projects that maximizes the overall value of the portfolio, which is the sum of the individual project's value as displayed at the bottom of the value column. An optimized portfolio is a portfolio that delivers the maximum return against a given set of constraints such as financial, resource, and risk constraints. As you will see in a few minutes, OPSI lets you essentially dial in your constraints to get an optimal portfolio. When you double-click on a project, it opens it in the choice form, and we can modify the data. The individual attribute values are entered into the choice value fields. And note that next to each attribute value field is a field for entering the percent uncertainty for each individual attribute. This indicates that the choice attribute value has an uncertainty of plus or minus the percentage entered.